Hello everyone, this is part 2 of topic 8 for exam 3, method of partial fractions. It's linear factors. This was our first page of notes. We saw improper fractions required long division, and we saw how the fact that combining two proper fractions gives a proper fraction, and decomposition is the reverse of this. And so then we saw an example where we decomposed by the method of partial fractions, and there were two ways to solve for the constants, comparison or elimination, and it seemed elimination was a lot easier. So we'll look at a couple examples now of, this is still case 1, what I refer to as linear factors. And so we have two examples of this, and that'll take care of this topic, and then we'll move on to topic 9, which is case 2 of partial fractions, when we have what I call repeated factors. Now, the first thing to do, no matter what, for all cases, you have to first factor the denominator. You don't care about the numerator, but you have to factor the denominator completely. So here you can see in the denominator we have the difference between two squares, two perfect squares, that is, x minus 3x plus 3, so that factors neatly. Because remember, the premise is that any polynomial can be factored into the product of linear factors and irreducible quadratics. So here's a product of two linear factors. So now we start with the method of partial fractions. So I'm just going to write PF, and what we do is we take out the integrand. So 1 over x minus 3, x plus 3 in this case, and we set up the decomposition. Now remember, there's going to be as many factors in the denominator as there are unique factors. There's going to be as many terms, I should say, in the expansion, in the decomposition, as there are unique factors in the denominator. So in this case, 2, one with x minus 3, and one with x plus 3. Now, this was a proper fraction to begin with, so each of these fractions must be proper, and since they're linear factors, the only thing that we could put above them to keep them proper would be constant terms. So we'll say a and b respectively, because we can't put an x up there, because if we put an x up there, it would no longer be a proper fraction. So then we create what I call the working equation, and we do so by multiplying by the least common denominator, which is the denominator on the left. And so on the left, we're always just going to get the numerator, and if we multiply, you should be able to do this mentally. Excuse me. I mean, if you literally have to show that you're multiplying x minus 3, x plus 3 by each of these terms, that's fine. But just mentally, if you multiply a over x minus 3 by this denominator, the x minus 3's will cancel, and we'll be left with a times x plus 3. And similarly, we'll have plus b times, we multiply b over x plus 3 by this denominator, the x plus 3's cancel, and we're left with b times x minus 3. Okay, so now we can start to solve for the constants. So we saw the two methods were comparison, which led us to a system of equations, or elimination, which seemed simpler. So I'm going to suggest at all times you use the elimination method first, and you just strategically choose values of x that are going to zero things out, so that you're only left with one constant to solve for. And you can go in here and you could say what's going to cause this to 0 and what's going to cause this to go to 0, and just pick those values. I always like to go back, as I mentioned in the last lecture, I always like to go back to the original partial fraction decomposition and force that particular denominator to be 0, because then I'll know that I'm going to be solving for the constant above it. So therefore, in this case, to solve for a, I could let x equal 3. And if we let x equal 3 into the working equation, we get 1 equals a times 3 plus 3. There's no need to show the substitution for 3 here, because obviously that's why we chose it, because 3 minus 3 is 0, and that eliminates b. So therefore 1 is equal to 6a, and a is 1/6. Okay, so then we're going to let x equal, now to solve for b, if I look back at the original decomposition, and I force its denominator to be 0 by choosing x to be -3, then I'll be able to solve for b. And into the working equation, plug in a -3 for x, we get 1 equals, no need to plug in a -3 here because that goes to 0, so 1 equals b times -3 minus 3. So 1 equals -6b, and b is -1/6. Okay, so now the result is that this integral of, I'll take the factored form, 1 over x minus 3, x plus 3 with respect to x, is now equal to the integral of, into the partial fraction decomposition, we replace a and b by the respective values. So a was 1/6 over x minus 3, and then plus b, which was a -1/6 over x plus 3. And that's all with respect to x. And then to make things simpler, let's separate this into two integrals and at the same time factor out these constant multiples. So we have 1/6 integral 1 over x minus 3 with respect to x, and then minus 1/6 the integral of 1 over x plus 3 with respect to x. And remember last time we mentioned that the major formula is going to be the integral of du over u, which results in the natural log of the absolute value of u. And that, of course, because we're dealing with rational functions or fractions, and denominators are not powers. If the denominators are powers, we're going to use u to the n, and we'll see that in subsequent cases. But here, no real need for a formal u substitution, because we could tell by inspection that it's going to work, because if we choose u to be x minus 3, for example, du is identically dx, so no modification by a constant multiple is necessary. And similarly here, if we choose u to be x plus 3, the du is again identically dx, so no modification by a constant multiple is necessary there. And when we integrate, we just simply get the natural log of the absolute value of their respective denominators. So integrating, we get 1/6 natural log absolute value x minus 3. I mean, if you want to go through and show the formal u substitution, that's fine, but I'd like you to be able to evaluate these simple ones by inspection. So similarly, we get 1/6 and then, or -1/6, and then the natural log of the absolute value of that denominator, x plus 3. And then we add our constant of integration. Now for me, you could stop right there. I just want to mention this one time. In the textbook, a lot of times what they'll do is they'll condense these logarithms by our log properties. So the natural log of, let's say, x minus 3 raised to the 1/6 minus natural log absolute value x plus 3 raised to the 1/6, and that's by our and we have a constant of integration as well. Okay, so that was done by the power property for logs in reverse, and then finally we could express this as a single log because it's a difference. So the natural log of a quotient, x minus 3 to the 1/6 over x plus 3 to the 1/6, and then finally plus our constant. So that extra work is not necessary. Just simply stop right here where I put the double bars, and that would be sufficient. Okay, so one more example, just to kind of firm things up here. Again, the denominator has to be factored. I'm going to factor for you because if you make a careless mistake in factoring, then it changes the problem completely. But here, first thing to look for when factoring, greatest common factor. X is common. Left with x squared plus x minus 6. We have x plus 1 over all of that with respect to x. Factor further if we can. And we can. This quadratic factors as x plus 3 and x minus 2. We have the x plus 1 in the numerator. Okay, so that's the correct factorization. And we start with the partial fraction decomposition. So take out the integrand, x plus 1 over x plus 3, x minus 2, now equal to, okay, remember you're going to have as many terms in the decomposition as there are unique factors in the original fraction. And so in this case we're going to have 3, one with an x in the denominator, one with an x plus 3 in the denominator, and one with an x minus 2 in the denominator. Oh, and if you had factored this x minus 2, x plus 3, it won't matter. It's all, the mathematics will always work itself out. And so at that point, what should go above these, because these are all linear factors, the only thing we could put above them is constants. So we'll say a, b, and c respectively. Okay, clear the fractions to create the working equation. So we're multiplying by the least common denominator, which is the denominator on the left. And so on the left, we always just simply get the numerator. Okay, and then if we imagine multiplying a over x by this denominator, the x's are going to cancel. Because literally, you could just cover up what's common and see what's left over. And so we have a times x plus 3, x minus 2. Then we'll have plus b. X plus 3's now cancel, so what's left over is the x and the x minus 2. And then we have plus c times, what's left there would be an x and an x plus 3. Okay, so you have to make sure that you copy down the... Okay, so now we need to solve for the constants. And as we saw last time, and this is guaranteed, if the denominators are linear factors, you can use the elimination method and it will always work. And then we'll see in subsequent topics what happens when the elimination method needs to be used in combination with the comparison method. But for now, take advantage of the fact that the elimination method works well. Okay, so to solve for a, remember we'll look back at the original decomposition, force the denominator to be 0. So if I let x equal 0, I'm going to be able to solve for a. In the working equation, make sure you plug in on the left-hand side as well. 0 plus 1 equals a times 0 plus 3 times 0 minus 2. No need to show a 0 substituted in for b here, or for x that contains the b, because x is 0, so that term goes to 0, and similarly with the term containing c, that term goes to 0 because x is a factor and x is equal to 0. So we get 1 is equal to, it's like negative 6a, so a is negative 1/6. Okay, now let's see if I want to solve for b. I'm going to look at this, and I'm going to say, alright, I want that to be 0, so let x equal negative 3. Again, don't forget on the left-hand side, you got to plug in a negative x as well. So negative 3 plus 1 is b times, see a negative 3 in for x here goes to 0, so no need to show that. Same deal with c. Negative b times negative 3 minus 3 minus 2. So negative 2 equals, let's see, that's negative 5 times negative 3, 15b. So b is negative 2/15. And then finally, to solve for c, we can let x equal, again, look up here at the decomposition, force its denominator to be 0 by choosing x to be 2. And we should be able to solve for c. Again, don't forget on the left, in the working equation, substitute in x is 2 plus 1, term containing a and the term containing b both go to 0, because x minus 2 is a factor, and we're letting x equal 2. So then into the term containing c, we have c times x is 2 times 2 plus 3. So we get 3 is equal to 5 times 2 is 10, so 10c, and c is 3/10. Okay, so I always like to rewrite. Now we're ready to go to the partial fraction decomposition. I always like to rewrite the original integral. I'll write the one in factored form. X plus 1 over x plus 3, x minus 2 with respect to x. And then into the partial fraction decomposition, we have the integral of, okay, back up here, a over x, so we'll replace a, negative 1/6 over x, plus b, that's a negative 2/15 over x plus 3, and then plus c is 3/10 over x minus 2. And that is all with respect to x. And probably most advantageous to separate that into 3 integrals in this case. Factor out the constant multiples as well. So negative 1/6 integral 1 over x with respect to x, minus 2/15 integral 1 over x plus 3 with respect to x, and plus 3/10 integral 1 over x minus 2 with respect to x. And similar to the last situation, a formal u substitution really isn't necessary. Well, first off, 1 over x, it's pretty much by memory, or it should be. Recognize that to integrate to be the natural log of the absolute value of x. But then for each of the remaining integrals, again, a formal u substitution shouldn't be necessary. If you want to, by all means do so, but you should be able to see mentally that if we choose u to be the denominator here, x plus 3, the du is identically just 1 dx. So that turns out to be the integral of du over u, which is the natural log of the absolute value of u. And similarly, 1 over x minus 2 the same. Choose u to be its denominator, and the du is identically 1 dx. So these turn out to integrate to be just the respective natural log, to be the natural log of their respective denominators. So minus 2/15 natural log absolute value of x plus 3, and then plus the 3/10 natural log absolute value, its denominator, x minus 2, and don't forget to add the constant. Okay, so that's it for case 1, linear factors, and we will come back for topic 9, which is case 2, repeated factors.